A gas is contained in a vertical cylindrical chamber capped by a frictionless piston. We are given the cylinder's diameter, combined mass of the piston and load, the local gravitational acceleration, and the atmospheric pressure. We are asked to find the total downward force applied to the gas, the absolute pressure of the gas, and the work done by the gas if the piston rises 1.7 feet, and the corresponding change in the gravitational potential energy of the piston load system. So the first thing we're going to do is label our diagram. So we have the atmospheric pressure pushing down on the piston. We have the mass of the piston and the load. Here is the height if the piston rises. And this is the diameter of the piston, which is 1.25 feet. We have, of course, the gas inside pushing up on the piston. So the first thing that we're asked to find is the total downward force applied to the gas. So this total force is going to be equal to the force of the atmosphere pushing down on it plus the force of the gravity, which is acting on the piston and the load. First, we'll find the force of the atmosphere, which is equivalent to the pressure of the atmosphere times the area of the piston. So our area, since the piston is a circle, is pi r squared, or pi diameter divided by 2 squared, which is equal to pi times our diameter of 1.25 feet divided by 2 squared, which gives us 1.2272 feet squared. Now we have our area. We can plug this in to get our force, the atmosphere, which is our pressure of 30.12 inches mercury per feet squared, times our area, which is 1.2272 feet squared. But we need to convert the inches of mercury into pound force so that it lines up with our other calculations. So we're going to multiply by our conversion factor, which is 70.73 pound force per foot squared, is equivalent to 1 inches mercury times foot squared. Now we can make sure that all of our units cross out, so our feet cancel here, the feet here cancel, and the mercury cancels, so we're just left with pound force. So plugging this in, our atmospheric force is equal to 2,614.3 pound force. Now our force gravity is equal to mg divided by g sub c. So plugging this in, we have 250 pound mass times the gravitational constant, which is 30.169 feet per second squared, all divided by g sub c, which is 30.174 pound mass per foot times pound force per second squared. Now making sure our units cancel, we have feet cancel here, seconds cancel here, and pound mass canceled, leaving us with just pound force. And this comes out to 249.96 pound force. So now we can find our force total, which is the force applied by the atmosphere, 2,614.3 pound force, plus the force exerted by gravity, which is 249.96 pound force, giving us the total force of 2,864.3 pound force. Now for part B, we are to find the absolute pressure of the gas. The pressure of the gas is equal to the total force pushing on it divided by the cross-sectional area. We've already found both of these numbers, so plugging in, we get 2,864.3 pound force divided by 1.2272 feet squared. But in order to convert to psi, we need to multiply by our conversion factor of 1 foot per 12 inches, and then square our conversion factor. This gives us that the pressure of the gas is equal to 16.21 psi. And it's absolute, so you can add an A. The final part, part C, is asking for the work done by the gas if the piston rises 1.7 feet, and then the corresponding change in the gravitational potential energy of the piston load system. So first we'll find the work done by the gas. So work is equal to the negative integral of pressure dV. But because we're at a constant pressure, we can simplify this to be the negative pressure gas times the change in volume. And volume is equal to the area times our height. So it simplifies that our work is equal to negative pressure of the gas times the area times the height. The pressure of the gas times area is equivalent to our force total. That can be derived from this equation over here. So our work is really equal to the negative force total times our height. This should really be change in height. Same over here. So calculating our work, we have a negative 2,864.3 pound force times our change in height, which is 1.7 feet. This comes out to negative 4,869.2 feet per pound force. The negative sign indicates work done by the system. So the work done by the gas is actually the inverse of this. So our work by the gas is just 4,869.2 feet per pound force. Now for the last part to find the change in potential energy. This is equal to mass times gravity times change in height divided by g sub c. Plugging this in, we get 250 pound mass times 30.169 feet per second squared, which is our gravitational constant, times our change in height of 1.7 feet, all divided by g sub c, which is 30.174 pound mass per foot divided by pound force per second squared. So checking our units, the pound mass cancel, the feet cancel, and then the second squared cancel. This gives us a change in potential energy of 424.9 feet per pound force. Zooming out now, that is the full solved problem.